So next up, we have Dr. Jernej Zidar, who is our Senior HPC Application Analyst at NSCC. So Jernej has a keen interest in computers, their inner workings and biochemistry for a long time. He was able to combine both through computational chemistry by first pursuing a degree in biochemistry, followed by a PhD for the work on amyloid protein beta and lipid graphs. So in 2011, he moved to IHPC to work on antimicrobial polymers, soon followed by a number of industry collaborations. And in 2019, he left academia to work at Akanan, where he benchmarked several MPI libraries on-premise and cloud-based. On-prem and cloud computer cluster running with and without Kubernetes. So at NSCC, Jernej spearheads the adoption of the commercial cloud and other strategic projects. Let's welcome Jernej on stage for his presentation on applications, specs, and Gromacs. Please.
Hi everyone. So you heard a lot about the hardware on Aspire 2A, what it has inside, what it doesn't have inside. You heard about Kubernetes just now. So I think it's very apt that at this point in this day, you hear something about applications, like what would you actually want to do with such a great machine? So in my short talk, I will talk about Spack and about Gromacs. So I'm very familiar with Gromacs. I've used it extensively before in academia to actually do science, but now I use it to test new hardware, be it on-premise like Aspire 2A or elsewhere, somewhere in the cloud. But first, let's spend a few minutes talking about Spack or Spack. What is it and what it can do? So if you're familiar with Linux, most Linux distributions have a package manager. So if you want to install, for example, OpenMPI, you would do, I don't know, on RHEL, you would use yum -i, OpenMPI, blah, blah, blah. In Debian, you would use dpkg or apt, and so on and so forth. So what Spack is aiming to do is to simplify management of high-performance computing systems so that you can easily deal with deployment of applications in systems like Aspire 2A, where you have, if you recall from 2 talks back, we have the Cray stack, Cray compilers, we have GNU compilers, we have Intel compilers, we have AOCC, and we have NVIDIA compilers, right? So, and there's that. Then we have Cray and Pitch, we have OpenMPI, and then on top of that, you also have various scientific libraries like crylipsa, you have FFTW, you have Intel MKL. And if you try to think how many combinations are possible, the number is staggering. So what if there was a system that would allow you to say, hey, I want to compile Gromacs using GNU compilers, use Cray and Pitch, and just because use Intel MKL. What if you could do that? So Spack aims to allay precisely that. It works. Installing Spack is easy. Spack is free. You just do a simple git clone, and it readily detects. Does this thing work? It readily detects all the installed compilers, both the ones that were installed by the vendor, and all those that have the -NSCC were installed by our systems team. Right? So everything looks really good. And you can try to install a simple application, right? You can you do a spec just to see what would be actually installed, and then you just issue a spec install, and hey, it compiles. So as you can see, I ran this command on a compute node, as you can see here, just to verify that the executable that I have actually works. Actually works. We don't know that. And to test whether it actually works, I just issued an ap run, gmx_mpi, md-run minus help, basically. It just prints out the help. And it actually works. So this was compiled. If we just go back, we can see that I used GNU GCC 11.2.0. I used H-reader lock was disabled. Anyway, it works. So what about that? If you turns out that Spack is pretty much a work in progress and you are critically dependent on other volunteers in the community or within your organization to write a recipe, how you combine all the compilers, the MPIs, the scientific libraries together and compile it in such a way that you get something meaningful out of it, something that works and doesn't fail while compiling, right? So what can I say? I see a use case for Aspire 2A, for Spack on Aspire 2A because we have such a big family of software that we have to support. The nice thing is users can install their own software. You don't need root privileges. You just run this, you can run Spack in your home directory, just as you would compile Gromacs manually or LAMS or NAMD, whatever, right? You can run it in your own directory and it's visible on the compute nodes, which is actually good. However, as I mentioned, every piece of software needs a specific build recipe, which can be a bit tedious, especially if you have software that's not really mainstream. So Gromacs is pretty much mainstream, LAMS is mainstream, but you have some very specific piece of code that was developed at IHPC, for example, that does not exist outside IHPC, then you may have a problem, which is a bit of a shame. However, this doesn't mean that we'll just give up, right? We will continue to evaluate Spack within NSCC, and hopefully we will be able to provide it to you as a means to allay your concerns, because coming from IHPC, I know I was often frustrated because the latest and greatest versions of Gromacs were not available, right? So this would be a great way to, instead of just emailing NSCC, which is great, by the way, you can just DIY it. Spack, install, boom, you have your own Gromacs, you have your own application. So I think that's one thing worth pursuing. And with this thought, I will conclude this section about Spack. I will talk, does it work? I will talk about Gromacs. Okay. What is Gromacs? I think we're all familiar. It's a molecular dynamics code. You can run simulations, you can do analysis, you can prepare inputs, and so on and so forth. And it's free. And it's a fairly simple piece of code. You can readily compile it on all sorts of exotic hardware, including, but not limited to ARM processors, etc., etc. Now, one reminder, that's the only hardware reminder that I will have, is that one node on Aspire 2A has 128 cores. If you think about Aspire 1, there are 24. So 6 times more cores per node, which is pretty cool. Now, Gromacs performance critically depends on the compiler that you use, the MPI library, math library that you use to compile, and the size and shape of the simulated system. By size and shape, I literally mean the size that you simulate. So if you have a cube, that's one type of performance considerations. If you have a square, or not a square, a sphere is something else. Also, if your system is homogeneous, so you have this, if you think about this cube, has just like water. Imagine a water cube, then it's another thing. And of course, what's most importantly is how many nodes, cores, or accelerators you can use for this simulation. So what I did for this presentation today, I compiled 3 different executables for Gromacs. I used Gromacs 2022.1. So I use Cray compilers, I use GNU compilers, I use Intel, I use Cray and Pitch because it's recommended. And then I use libsci and I use MKL for Intel. And I used 3 different benchmarks of 3 different sizes. This one is very small, of course, 140,000 atoms. This is 1 million, and this is 12 million atoms, more than 12 million atoms. I wanted to see how the application scales, what is the performance, but also to show you that on Aspire 2A, you don't really have to limit yourself. You can think big. 12 atoms, 5 years ago, 12 atoms would be unthinkable. Like even on Aspire 1, or even if you would try to do it in the cloud, 12 million atoms is huge. But on Aspire 2A, you can actually think, oh, I can actually solve this important scientific problem if you limit ourselves to science or to material science, for example. You can actually really think big. So what I did, so apart from compiling, I ran 5 runs for each executable, and I ran it from 1 node all the way to 256 nodes. So 256 nodes, if you recall from the previous presentations by Paul and by Tagu, this is basically one whole CPU rack. I didn't evaluate the performance on GPU nodes just yet, because that's another set of considerations. And then what I compute was just I collected performance number, and I computed average, standard deviation, and then I computed the speed up and parallel efficiency. I will just quickly go through these slides, because I just wanted to show that for the first time, you can actually encounter a problem whereby your system is not big enough. It cannot fully saturate the system. And that's a really, really pleasant problem for you, our users, our researchers, to have. Because you can, as I said, you can think big. So as you can see, for the ion channel input, running more than 16 nodes makes very little sense. You're wasting performance, one, and once the system is fully loaded by other jobs, you will be wasting your time in the queue, right? Because waiting, if you submit a job that requires, for example, 16 nodes, it will take longer for it to run than if you ask for 8 or 4, right? And we can see similar trends, like this is for the speed up, for the parallel efficiency. You can see that it really drops because your system is just too small. And we can see the similar trend for the 1 million atom benchmark. This is satellite tobacco mosaic virus. Again, there's no point going beyond 32 nodes, right? You can, of course you can, but why would you? It will take your job way longer to run. And again, similar, the parallel efficiency significantly drops. And here we have the 12 million atom benchmark system. You can see that even this one, it could actually be even bigger, and it would still run well, right? So this is at 128 nodes roughly, and you can see that it could be even bigger. So, of course, key takeaway is that for small systems, you don't have to use a lot of nodes. You can use way less nodes than you did on Aspire 1, and then for medium, you can use, let's say, up to 32, and for large system up to 128. But the key takeaway message is that you don't have to limit yourself. You can really, instead of right-sizing your problem so it fits the compute, right? You don't have to, for example, I will give you a plastic example, is instead of simulating just a tip of a COVID spike, coronavirus spike, why not simulate the whole spike? You can actually do that. You can see how it behaves in different environments, how it reacts to different potential drugs or whatnot, or you can simulate a huge chunk of a new novel material that has some properties that you're interested in, right? So this is all that I had to say. Please avail of this new system that is coming up. Don't limit yourself. Thank you.